Go for it.
Yeah. Good evening, good afternoon, and good morning to all our friends attending from different parts of the world and to our speakers. This is our third plenary session. This plenary session contains two keynote lectures. The first one would be delivered by Professor Gopal and the second one by Professor Tauhata. This session will be chaired by Professor Swamisaran and co-chaired by Dr. Ramakrishnan. Before I hand over the session to our chair and co-chair, I would like to briefly introduce them. Professor Swamisaran is well-known personality. His book is very popular. Most of us all studied his books on soil dynamics. Apart from that, he has written several other books. Even till now, he's very active. He's still, I just came to know a few months back, he has completed another book writing. So for just sake of formality, I will just brief about him. Professor Swamisaran, Emeritus Fellow, retired from Indian Institute of Technology, Roorkee, obtained his PhD in 1969. He established teacher, researcher, and active consultant. He is the recipient of Khosla Research Award 4 times and IGS Award, including prestigious Kupulman Award and also awards from ISET, I.I.Sc and I.I.Scms. He has guided 29 PhD theses, 84 master theses, published 208 research papers and 8 books. He has initiated research work on reinforced soil, analysis of foundation using constitutive laws, and dynamic analysis of retaining walls. He has provided consultancy to more than 300 projects of national importance. He visited the UK in 1974 under exchange program and IIT Bangkok as visiting professor in 1987. A national conference was organized at IIT Roorkee in 2007 to honor him. Considering his contributions, Indian Geotechnical Society conferred honorary fellowship on him in 2011. With this brief introduction, I welcome Professor Swamisaran to this session to chair.
Thank you, Ravi.
Thank you, sir.
That you have given a chance to act as a chairman of this session in which 2 learned speakers are with us.
Yes, sir. Sir, let me also introduce our co-chair, sir, Dr. Ramakrishnan. Yeah. Dr. Ramakrishnan is currently working as a senior grade assistant professor at the Department of Civil Engineering, Amrita Vishwa Vidyapitham, Coimbatore, India. He is a PhD from the Indian Institute of Science, Bengaluru, and has extensively worked on geotechnical earthquake engineering, focusing on seismicity of Himalayas. His key areas of research include geotechnical earthquake engineering, slope stability, and soil stabilization. He has authored numerous research papers in peer-reviewed international journals and conferences, and is a reviewer for various international journals. He is a passionate researcher and has carried out relevant and impactful research at this young age, which was well received with about 200 citations. With this brief introduction, I welcome Dr. Ramakrishnan.
Thank you, sir. Namaste. Thank you for inviting me to co-chair this session. I'm extremely, I'm extremely honored to be here alongside Professor Swamisaran to chair this session. And I would like to extend my thank you to all the organizers. Thank you.
Thank you, Dr. Ram.
Yes, and now I request Professor Swamisaran and Dr. Ramakrishnan to take over the charge of the session. Please,
Thank you very much. Thank you very much. Now, actually, as I just mentioned, there are 2 speakers in this session. Both speakers are very learned one. and I will request them humbly to confine their presentation for about 45 minutes so that we have some time for discussion also. The first presentation will be by Professor Gopal Madhurishi. I will briefly introduce to the audience about him. Professor Gopal is a professor of civil engineering at the University of Cambridge, director of Schofield Center, and also head of Geotechnical and Geo-Environmental Group. He has over 25 years of experience in the area of soil dynamics and earthquake engineering. His expertise extends from dynamic centrifuge modeling to the time domain finite element analysis of earthquake engineering problems. He has an active interest in the areas of soil liquefaction and soil structure interaction. He provided leadership to earthquake engineering field investigation team. He was awarded many awards. To name the few, TKHA Award 3 times, Shamsher Prakash Award 2 times, Medical Innovation Award, IGS-AML Biennial Award, and Bill Curtin Medal, IGS Agency Biennial Award, etc. He has published more than 400 papers and also authored a book on design of pile foundation in liquefied soils. With this brief introduction, I invite Professor Gopal for his presentation.
Thank you very much, Professor Swamisaran. It's a real honor and privilege to be introduced by you. As the chairman has said, Ravi was saying, we all grew up studying your book. So it's really gives me a great thrill that I was introduced by you. Let me start by sharing the screen and hope it all works. Are you able to see the screen?
Yes,
My
sir.
screen or?
Yes, yes.
Okay, very good. So I need to go into presentation mode and try to not see all the faces in one go. I'll try and keep it to the time as much as I can. And in case you feel that I'm overrunning, please stop me, Professor Swamisaran, and I'll wrap up at that point. Today I'm going to speak about advances in modeling of soil-structure interaction problems. That's been the topic. And I want to share with you some of the recent research we've been doing at Cambridge on this. The layout of the lecture is going to be like this. I'll start at the very basics of what do we mean by soil-structure interaction. We then shall look at dynamic soil-structure interaction. I'll briefly introduce dynamic centrifuge modeling. A lot of you must have heard me do this before, so I'll try and keep that brief. And then I'll go pick on a couple of recent work. One is looking at retaining structures. And for today, I picked anchored retaining walls and retaining walls with the structure behind on the backfill side and look at their interaction. The other problem I picked is the foundations for wind turbines. This is a very, very hot topic in the UK, but now it's picking up pace both in Japan and in Taiwan, and very soon it will be along the Californian coast as well, all highly seismic areas. So we started research on looking at the seismic behavior of these offshore monopile foundations and also some onshore raft foundations. And I'll end up with a brief summary. Now, as you probably heard before, the centrifuge modeling to investigate earthquake loading on civil engineering infrastructure has established itself as a very useful technique. It's very useful because you can test on small scale models at high gravity in a centrifuge, and you can understand the behavior of these structures without the need to actually wait for a real earthquake to happen and damage civil engineering infrastructure. So, and also you might have come across this before, that the dynamic centrifuge modeling has been very widely used to study liquefaction problems. There have been relatively less use of this technique to look at the soil structure interaction problems. And in a way, that's what I'm going to focus on today, the soil structure interaction without liquefaction, and also some cases where there is liquefaction of the soil. Okay, by way of introduction, what is soil structure interaction? Soil structure interaction between structures and is the interaction between the structures and soil during a loading event, such that the response of one is influenced by the other. Let us consider a very simple example of a cantilever sheet pile wall, a retaining wall, as shown in the figure. And normally it's easy for us to identify the active wedge and the passive wedge. And the active wedge causes the disturbing force, marked with the yellow arrow here. And the passive wedge provides the resistance, marked by a yellow arrow going from left to right. Now, clearly, how much force is applied on the retaining wall depends on both the wall stiffness and deformation, of course, and the soil stiffness and deformation. The reason is that depending on the wall stiffness, it will undergo some amount of, say, bending and undergo some deformation. And the amount of strain mobilized behind the wall and in front of the wall is a function of this. And depending on how much strain is mobilized, you mobilize the passive pressure, and therefore the whole wall comes to equilibrium under the action of both of these components. So both wall stiffness and deformation and soil stiffness and deformation are important, and therefore it's a classical soil structure interaction problem. Similarly, we can look at dynamic soil structure interaction. Following on from before, it is the interplay between the structure and the soil foundations during a dynamic event. And just like the static SSI, the dynamic SSI occurs because the response of one is influenced by the other. So both are important for us. Now, if you consider a structure on a soil bed, and let's suppose for simplicity, it is just a simple raft foundation, and that the soil layer extends to infinity in the lateral directions, that is, it's a semi-infinite half space. Now, if you, once the earthquake loading occurs, the rocking of the structure will occur about the center of gravity of the structure. And this results to the stamping of the feet on both sides. This causes a variation in the vertical stress, and proportional to the vertical stress that's being generated, the stiffness of the soil changes, and therefore that changes the properties of the soil, if you like, and that affects how the structure will respond. So the dynamic behavior of the structure depends on the stiffness of the structure. Let's say it's a function of the flexural stiffness, the height of the stories, etc. And the stiffness of the soil depends upon the Young's modulus, shear modulus, word ratio, and the effective vertical stress, etc. Let's look at a simple example. Suppose here I'm going to show you a couple of pictures. There are two experiments. It's a simple portal frame model that has, you can test this on a fairly rudimentary shaking table we have. And you can shake this about, firstly, by fixing it to the ground so that only structural vibrations occur. And next, you can make a bed of sand, put the structure on the top, and shake it. We are monitoring the accelerations at every floor level. So the amplification factor, just let's define that as top floor acceleration by the input acceleration to the table. If you do that, and in the two experiments, you can get responses like this. At the top, in the top figure, you can see that the structure with a fixed base responds with a peak response at about, let's say, 3.2 hertz or something. For the same earthquake, when the structure is placed on the sand, the natural frequency drops and the peak response also drops. So you can see the natural frequency in the bottom figure has come down to about 2.3 hertz, and the amplitude amplification ratio also has reduced. This is expected because soil acts as a damper. This is a very, very simple way to show that the response of the structure actually depends on what's below the structure. Now, of course, that's a very simple experiment. Let's try and extend this to a single degree sway frame structure. Let's say it's placed on a sand layer. Now, the soil around the foundation is going to interact with the vibrations of this structure. And let's suppose we're applying the earthquake loading at the base, as shown by the bottom arrow. Now, here is a video from a 50G centrifuge test we have carried out, and you can see the stamping of the feet, as I explained earlier, when the earthquake occurs. Now, clearly, in order to see this, we had to record this video at about 1,000 frames a second during a 50G centrifuge test. So we have a fast camera that can do that. Now, looking this image itself is, okay, we can see now how the structure and the soil are interacting. But what's more interesting is to actually look at, use those images and apply the particle image velocimetry to it, and then you can obtain the soil deformations during the earthquake, as indicated by the arrows here. If you are more interested, there's a paper we have written some years ago now in Geotechnical, which you can follow. But the important point is that we are able to get the soil deformations below the foundation of a structure and clearly see the interaction between the two. Now, I briefly mentioned there that we use centrifuge testing. Let me introduce the basic principles. As I said before, I'll go through this fairly quickly. Centrifuge modeling is very simple. You basically build a physical model which is n times smaller than the actual prototype you're testing, and test it in an increased gravity field of the centrifuge where the gravity is n times larger than 1g. If you do that, then prototype stresses and strains are recreated in the model. Therefore, the soil will respond with the right stiffness more than anything else. And because we are capturing this right stiffness, that means we are capturing the nonlinear behavior of the soil correctly. This won't happen if you're trying to do a small scale test like I have shown you in the shaking table experiment earlier on. This is the reason why we need a centrifuge to do this. But in order to create an earthquake loading, we need to apply lateral shaking for models that are flying around in a centrifuge. In our case, the model is flying at about 200 miles an hour. So while it's going around in the centrifuge, we need to be able to shake it. For this, you need fairly powerful earthquake actuators. Here is a picture of a centrifuge. It's fairly old. It's built in 1975, and it's a fantastic machine. It's about 10 meters in diameter, and we call it the Turner beam centrifuge after Philip Turner, who designed the facility. As I explained, by doing this, we'll create the prototype stress and strains. And we also need to have these specialist earthquake actuators and model containers to minimize the boundary effect so that we capture the semi-infinite extent of our soil. The principle of centrifuge modeling, if you're interested, it's very easy. It can be done literally on the back of an envelope. And if I were to consider just a block whose dimensions are LB and H, the vertical stress exerted by that block is going to be mg over LP. And let's say the strain below this block is defined by some characteristic length alpha. So the strain will be delta alpha over alpha. So change in length over length. If I want to do the same thing for a block that is the same block that is scaled down by a factor of n, so the length is L over n, the breadth is B over n, and height is H over n, then the mass of the block is going to be m over n cubed because you squashed it in all dimensions. And if I increase the gravity by a factor of n, and so I'm applying ng in the vertical direction, and if I recalculate my vertical stress, it's going to be m over n cubed times ng over L divided by L over n times B over n. So you can see I can recover the same vertical stress as in the bigger structure, bigger block. Similarly, the strain will also come out to be the same. So the principle of centrifuge modeling is very, very easy to understand. If you're interested in more interested in this, you can look up the book I have written in a few years ago. As I said before, we need some specialist earthquake actuators. Let me introduce that. And we also need to have the scaling laws which link the behavior of our model to the prototype. Most of these scaling laws are fairly simple to derive. For example, length, obviously we are scaling everything by a factor of n, and therefore mass is 1 over n cubed. Stress and strain are 1 as required, and other properties we can very easily derive. When it comes to dynamic events, the time scales is 1 over n, which means the frequency of the event needs to be increased by a factor of n. And similarly, the acceleration goes up by a factor of n as well, which is consistent with the increase in gravity. The first earthquake actuator that I was involved with was this in the development of the earthquake actuator was this stored angular momentum earthquake actuator. This is a very cheap and cheerful earthquake actuator. You have a cheap Italian motor that can store energy into a flywheel, just like in your car. And then the energy that's stored in the flywheel is transferred to the shaking of the model container. And this is a very, very robust machine we built. And we need the only critical component here is a fast acting clutch, because the clutch needs to come on to grip the moving part and the non-moving part in less than about 10 milliseconds. With this, we could apply earthquakes of any frequency we want. Here is an example of a 1.8 hertz shake. You can see at the top. We can also switch off the motor once the clutch engages and run it down. So you can get a swept sine wave through this. Of course, the modern day fashion is to be able to apply realistic earthquakes. So we built this more expensive and all singing, all dancing servo hydraulic earthquake actuator. This is able to follow any input motion you give to it. For example, the Kobe motion is shown on the top that was obtained using this machine, and the Imperial Valley motion, which is a very long motion with very high frequency content. It's able to successfully reproduce. You also excuse me, need specialist model containers. Here is the laminar box, which is able to, it's almost has no lateral stiffness. Therefore, the soil can move wherever it wants to. The length of this corresponds to 40 meters, depth is about 20 meters, and width is about 14 meters. This is at 60 G. And we have other model containers which are even deeper and can go up to 25 meters at 60 G, or even deeper if you test it at 80 G. Now, if you look at these dimensions, these are much, much larger than even the largest shaking table there is in the world. You may have heard from Professor, my friend Ahmed Al-Gamal, who has the very large shaking table in San Diego, and that is a fantastic facility. And even that cannot take, our models are at the prototype scale are bigger than his. But of course, he can do a lot more detailed physical models of the structures and so on. So there are pros and cons. Here is another container where we have a glass side. The one I showed you earlier is taken using this one, where we're able to see what's happening to the soil during the shaking using a fast camera. Okay, that's all the kit we have developed over the years. And I'm going to now focus on the actual problems we have studied using these recently. The first one I picked was the modeling of anchored steel sheet pile walls. This work is done with a PhD student, Alessandro Fusco, and my colleagues, Giulia Vigiani, and we had an industrial partner, Cecil Prum of ArcelorMittal. So obviously, with ArcelorMittal, they're interested in steel sheet pile walls. And one of the key cases is this anchored steel sheet pile walls used as retaining structures. And you can see them, I put some figures in here, where typically you have water tables slightly lower, and you try to anchor them some distance away into the back. Obviously, these things can fail post-earthquake. You can have a local failure where the whole system can simply translate horizontally, or you can have a global failure where you involve the backfill soil to fail as well. So you can either pull the anchor through with the anchor sheet in the back, as seen on the top, or the whole soil can move on the in the bottom. So those are the, you can guess these are the failure mechanisms. But is that what's going to really happen? Let's have a look. So we use a centrifuge facility and this transparent box. And here is a camera, the fast digital camera, that is looking at the steel, the anchored sheet pile walls from this side. So the shaking is happening in the direction parallel to the base of the model container. So you can, I'm going to focus on two particular tests. One is AF03, where we have this anchor length of about 17 meters at prototype scale, and it's embedded at a depth of about 0.5 meter. In the second case, the length of the anchor was reduced to 12 meters. Also, the point of anchor in the first test is about a third from the top. And if you know the soil mechanics, you obviously won't do that. You would attach it at the bottom third point at about a depth of 1.25 meters. Therefore, you have an inclined anchor. We are able to, and the cross-sectional views of the pictures look something like this before any earthquake was applied. These images were taken, obviously, in flight. There are lots of instruments. I'm not going to spend too long on this, but because the data is presented in a very visual format. But as you can see, there are a lot of instruments to measure the accelerations within the soil bed, the settlements, as well as the anchor force with a load cell in the anchor line itself. So we're applying the input motion at the base. The left-hand one is the AF03, the right one is the AF04. And the input motion is about the same for both. And it's about, say, something like 0.3 G or thereabouts. So that is transmitted through the soil, and you get to the top, and you can see that the acceleration obviously is changing, and we're also able to get the force within the anchor as seen here, and there's clearly some residual force being generated in the long anchor compared to the short anchor. More residual force in the long anchor than the short anchor. So this is the real data presented at prototype scale. Okay. Of course, if you're designing these walls, you're interested in the bending moments and how do they change. On the top, you can see the bending moments observed in the wall for the AF03. And when you have a short anchor, clearly you got larger bending moments. You can look at either the maximums or the residual values. In fact, the residual value of the bending moments are pretty similar for both, but the peak bending moment is larger in case of AF04. The dynamic moment is larger for AF04 with short anchor length. Okay, what about deformations? The displacement of the walls are marked on the right, and you can see earthquake after earthquake, the wall is trying to move outwards as you would expect, and it accumulates the displacement because the wall obviously can't go backwards. What's also interesting is to see what this anchor wall is doing at the back end. So you can see initially it started almost straight, and with successive earthquakes, it is rotating. Because we are pulling it at the top third point, it makes sense that the anchor plate rotates in that direction. When it comes to AF04, you can see that the anchor wall is rotating. The main wall moves outwards as you would expect, but the anchor wall is actually not rotating that much for most of the earthquakes. Only when we applied really large earthquake, it did rotate a little bit backwards, which is a very good thing. So we'll expect for the top wall to have some kind of a local failure, whereas the short anchor wall to have a global failure. You can also get the displacements at different locations. You can get these in the prototype scale. Clearly, the short anchor gave rise to almost half a meter of movement. Cycle by cycle, you can see how it's evolving. Whereas when it comes to the long anchor, the movements are about half, 25 centimeters or so, a quarter of a meter. Okay, that's all good. Because we are having this fast camera taking images, we can do the PI view on this. And here are the contours of the horizontal displacement. And from that, you can also work out the shear strains and plot it. So these are the shear strains are computed from the displacements, which is fairly straightforward to do. Now, clearly, you can see when the anchor length is long, as we expected, the failure happens. The displacements are largest just behind the wall and also just in front of the anchor plate. Whereas when the anchor length is quite small, you can see you got a global failure where the whole thing is trying to move with large displacements happening all over. And you can also identify the boundary between where the shear strains are really concentrated. So it's kind of straight from the horse's mouth, as it were. You can get exactly what the failure mechanism is. So in summary, the deformation mechanisms behind the anchored retaining walls were investigated. The difference between the wall deformation and when the anchor length is changed were identified. The deformations of anchor wall changes depends on the anchor location, and the global and local failure mechanisms were clearly obtained. So that's a nice piece of work. We're of course doing the analysis on this, and more publications will come, I'm sure, as we go along. The next one is more recent work. This is all post-COVID lockdown. So I wanted to share this with you. It's a quite a nice thing to look at, where you tend to increasingly we're having structures coming very close to retaining walls for especially in the urban environment. Here is a picture where you can see a big structure next to a fairly deep retaining wall of about 15 meters or so. And what happens if an earthquake happens to these kind of structures and the retaining walls? So clearly it's a big soil section traction problem. Not only you got the retaining wall with the backfill, but you're putting a big structure behind it. You can also make a little analytical models of these things where you simplify the structure as a portal frame with a eccentric mass on the top and model it as a single degree freedom system just to get the initial natural frequency and so on. So we did two things with this. One is we ran the numerical analysis using Swandine, which is a finite element code, with and without the structure in place. So on the left-hand side, there's no structure, just the retaining wall. On the right-hand side, there is the structure in the backfill side. And the foundations of this structure are just strip footings separated by each other, as you can see in this figure. Side by side, we're also running the centrifuge stress of this, where the wall itself, the cantilever wall itself is strain gauged, so we can get the bending moments for it. We can also monitor what's going on with the structure. So with this, in the right-hand side, you can see the physical model of that. First thing is, because we are doing a numerical analysis, we can obviously get the horizontal stress contours for both cases. So on the left-hand side, you can see you've got the passive pressures developing at the base of the wall, which are clearly much larger when you have the structure. That part is fairly uncontroversial. Of course, once you got the infinite element analysis, you can get whatever you want. So we got the lateral earth pressures, see how they compare with the, say, Coulomb's active and passive pressures. And you can see the Coulomb's, because Coulomb's theory gives you a limiting earth pressure, you can see that the actual earth pressures mobilized as predicted by the FE analysis are much smaller than the triangular which you imagine, because the soil does not get to the amount of passive pressure you get depends on how much strain you mobilized. If the soil is not straining all that much, obviously your passive pressures are not going to get anywhere near the Coulomb's limiting earth pressure. Similarly, we can get the active pressures behind the wall. We can do that and compare what's happening when there is structure and when there is no structure. And you can see that on the active side, when there is structure, there's a bigger bulge because of the presence of the structure. Whereas when there's no structure, the yellow markers show very little variation from top to bottom. They're just triangular with depth. Similarly, we can get the bending moments, as you can see on the right here. These are normalized bending moments we're plotting. I do ask your apologies for the following slightly weird sign convention, which is followed by our undergraduates here. Irrespective of sign convention, you can see when there is no structure, the bending moments are smaller, and when there is structure, the bending moments in the wall are much larger. So clearly, there is a big effect of having the structure in the back. No prizes for guessing that. But these are all static analysis. But what happens when you apply earthquake loading? So we applied these earthquake motions at the base. Again, this is all still numerical, I must insist, and you can follow what's happening on the left hand. So we are considering two cycles. One is the first cycle, and another cycle in B is towards the end of the earthquake. And what you can see at a shot in the top, 4 figures on the left, is that the bending moment with the structure is larger than when there is no structure, even at any point of the cycle. And also, as the earthquake progresses, it seems that you get residual bending moments building up. And by the end of the earthquake, you can see much larger increase in the bending moments where there is the structure in the backfill compared to when there is no structure. So this is quite interesting. That means that if you have the structure, cycle on cycle, you build up these bending moments and they stay there with you for a long time. And especially if you're expecting multiple earthquakes at the same site, say some small earthquakes and large earthquakes, your walls are going to see increasing levels of bending moment. And that's worth knowing. When it comes to experiments on this, you can, of course, use this PIV technique and get the displacements, just like what we did with the anchored steel sheet pile walls before. You can see that the displacements behind when there is no structure case are largest, obviously, behind the wall at the top, and they kind of decrease as the contours are showing into dark blue, which means there is not much movement at all. When it comes to the structure, this pattern completely changes. And this is the nice and controversial bit here. Because I got the strip footings behind the retaining wall, it seems that these soil deformations are quite localized, especially underneath the right footing. And the left footing is also seeing a bit of displacements, but not as much. But you can see there's the wedge, if you want to call it that, of deformation is much more narrower when there is structure. This somehow indicates that the placing the structure is kind of stabilizing my soil, which is an interesting observation, which I wouldn't have guessed without doing the experiments and seeing these results. So that is a fun thing to know. Of course, from the experiments also, we can measure the bending moments. Again, we're plotting the same way. Here, first the envelope of bending moments here with and without the structure, and clearly having the structure gives you a larger bending moment. And You can also look at the residual bending moments after a strong earthquake. So this is nice. Of course, we can get the rotation of the wall and that of the structure, and clearly the structure suffers a lot more rotation when the wall moves out, because it's losing the soil from the right-hand side foundation. So the whole structure tends to rotate towards the wall. So this is all quite interesting and new. So if you're more keen, there are one publication that you can already download and have a look. That's on the numerical modeling of structures adjacent to retaining walls. And the other one is still under review. So hopefully that'll come out soon. But in summary, the presence of the structure on the backfill side of a retaining wall affects both the static and dynamic bending moments. I hope I demonstrated that. The backfill displacements are altered by the foundations of the structure, and this is a very clear indication of soil structure interaction case. So I've got two more things to talk about. One is the offshore monopile foundations, working with my PhD student Juntai Seong and my colleague Dr. Christel Abadi. I tried to go quickly here. I believe I still have about 10 minutes, Professor Swamisaran, I hope. Do stop me if I'm overrunning. The monopiles are very interesting because they're really large circular steel piles, and these are preferred by the construction industry to support offshore wind farms, especially in the UK. And these are about, they're getting bigger all the time. They're about 8 meters in diameter in today's designs. And you can see a person standing next to a large monopile there. So the objectives of this particular research was fairly straightforward. What we want to see is to look at the pre and post earthquake lateral capacity of these large piles. Also to apply a swept sine wave motion to identify the natural frequency in flight, and apply a strong earthquake at its natural frequency, 2 times the natural frequency and 3 times the natural frequency. We want to measure the dynamic bending moments in the monopile, also identify the dynamic response of the tower later on. So the cross-section of the model is fairly simple. We are looking at layered configuration, which is quite typical. So the monopile goes through a loose sand of about 6 meters deep, and it is embedded into dense sand, which has a relative density of about 90%. And the total length of the pile embedded is about 12 meters. This is slightly on the lower side. The real piles are a bit larger, but as an example, this is fine. We also have kit on the top, which are 2 actuators. So we use one of these piles to push it out to get the capacity, lateral capacity of the pile before any earthquake is applied. Then we do all the earthquakes, and once all the tests are done, we push over the second pile to get the post-earthquake lateral capacity. That's the plan. So we've got 2 actuators and 2 pile setups here. So these are the 2, how they look in reality. So we're modeling the mass, the overhead mass using these brass weights on the top, and the piles themselves are going deep below. And here's a close-up of the same thing with these actuators in physical form. And these are taken obviously with the model on the centrifuge itself. So the first business here is to apply a sine sweep and see what the model does. So the sine sweep is a fairly small earthquake we're applying, about 0.05 G. And firstly, in the dense sand layer, the lower dense sand layer, not much happens. You can see there's a bit of amplification, but nothing to write home about. When it comes to loose sand layer, you can see that the soil obviously is amplifying the input motion, and you can see the increase in amplitudes as you get to the surface of the soil, as you would expect. However, if you look at the response of the tower itself, although I'm putting no more than 0.05 G here, the top of the piles are responding with fairly high acceleration when you are hitting this with the because you are picking on the natural frequency of the pile soil system. So using this, we identify its natural frequency, and we do a FFT clearly to get this, and this is about 0.5 hertz, let's say. It's less than 0.5, but call it 0.5 for now. And we hit this firstly with the Kobe motion, and again, you can see the tower response is fairly small. We're applying some 0.15 G of scaled Kobe motion, and nothing much happens in the tower. But if I hit it with the same 0.15 G of sinusoidal motion, but now at the natural frequency, you can see the response of the tower has gone mad. It's more than 0.6 G. So clearly, natural frequency is a bad thing. But if I hit the same thing with, you can also get the bending moments when these things, when this was applied, when we applied an earthquake at natural frequency, and see what are the peak bending moments are. And if you hit the same structure with 2 times the natural frequency, you can see the response is completely right. I'm applying the same 0.15 or 0.2 G, and you can see the tower is not, the top of the pile is not responding at all, because you're 2 times further away from the natural frequency. Then we did this pushover test, and you can see that this pushover test before and after, you can see that the capacity of the okay, so we are plotting horizontal displacement on x-axis and horizontal load on the y-axis in meganewtons and
Gopal,
meters.
5 minutes more, please. 5 minutes more, please.
Okay, thank you. So let's look at the normalized version of this, where you can see that the if I plot the about say up to 0.16 of some kind of normalized displacement, you can see that the post-earthquake, I can get quite a big increase in the peak load compared to the pre-earthquake situation. But the key is that the initial stiffness has gone down. And this is very interesting. But of course, we need to be a bit careful here, because the dynamic response of the system is quite large. Is when an earthquake frequency matches the natural frequency of the soil monopile system. But during realistic earthquakes, of the earthquake frequency range, the response is quite small. The pushover capacity increases, but the initial stiffness is smaller. This has serious consequences in the design phase of monopiles in seismic regions. And we are, of course, doing a lot more work on this, including soil liquefaction. So last thing is the onshore raft foundations with wind turbines. And this work we're carrying out with my colleagues, Juntai Seong, Dr. Haig, and Professor Vijayani, and in collaboration with Adani Green Energy Limited. And this is a case where we're looking at an onshore raft foundation on liquefiable soil. So I'm going to talk about 2 tests. One is an ATG test, and both are ATG tests, but one without any ground improvement, and another one with stone column array of 9 by 9 stone columns. So there are nearly 81 stone columns here. So the first one is simply, again, layered soil, the top liquefiable layer with a lower, denser, non-liquefiable soil, if you follow that. And here are some details of how we made the model, but that's not important right now. So in the second test, we have these drains going all the way through the loose layer into the dense layer. And we constructed this quite painfully, as you can see in the bottom pictures, where we drive aluminum piles, fill the aluminum pile with the coarse sand, and then you tamp it to get the right density. So that's all in model making. We also measured in flight the soil stiffness using air hammer, and we could show, we could see where the loose sand is transitioning into dense sand in that way. Okay, firstly, I'm going to talk about Imperial Valley, where you got a very small earthquake being applied, less than 0.05 G. And you can see the foundation, there's a bit of amplification, but if you look at the tower, it picks up the natural frequency of the tower, and it starts to isolate quite a lot. And if I were to plot the displacements of this, you can see the tower displacements appears to be quite big. But if you actually look at the magnitude, it's still at prototype scale, only 0.05 or 0.4 meters. So the actual lateral displacements are negligible. What about the settlement? The biggest concern for these things is the settlement and rotation. You can see I got a bit of settlement of the surface and a little bit of settlement on the of the foundation itself for a very small earthquake, and the rotation is almost negligible. However, when I apply a bigger earthquake at 1 hertz, then you can see two interesting things happen. That the tower itself does not respond very much when it comes to the first AGL 1 case where there's no ground improvement, and the accelerations are reduced because of soil has liquefied. Whereas if you look at the drained case, the accelerations are much larger, but that also confirms that there has been no liquefaction. That is one good thing. Similar to before, we can look at the displacements. Now you can see that the tower is not displacing at all because it does not participate in these vibrations. Its natural frequency is much lower than the 1 hertz we're applying. But if you look at the settlements, which is the most important thing, when you have just in normal soil, just in 1 earthquake, it has settled more than 0.25 meters. But when you improve the ground with the drains for the AGL3 case, the settlements are much smaller. Similarly, if you look at the rotations of the foundation, which is a critical performance criteria for these things, anything more than half a degree you cannot have. You can see for AGL01 case, the rotations have gone to almost 1 degree post-earthquake, whereas when we have drains, the rotations are much smaller. And here are some post-test pictures where you can see what happened to the drains before and after, and also the soil layer itself when it before and after. This is a complex problem, but in summary, what we can say is that the onshore wind turbines on liquefiable soils are very susceptible to settlements and rotations, and installation of stone columns seem to have mitigate this most of the settlement damage. And however, the price you pay is that there'll be increased structural seismic response due to increased stiffness, and there is an optimization you can make between how much settlement you can tolerate and how much accelerations you're willing to accept. Okay, in summary, I hope I have demonstrated in the last 50 minutes or so that the dynamic centrifuge modeling is a very neat way to study soil section traction problems. We're able to use this technique in more and more sophisticated structural and soil models. Today I have used anchor sheet pile walls to investigate the using PIV to identify global versus local failure mechanisms, and the later shown to afford a lot more resilience against strong earthquakes. The structures in close proximity of retaining walls, again, some very interesting observations came out of that, both in terms of static and dynamic bending moments. Offshore monopiles, where you can see that it's an emerging area of research, but already we can see what difference we can bring by understanding these things. And finally, onshore wind turbines, where ground improvement seems to play a very nice and important role in controlling settlements and rotations. Thank you very much. Any questions?
Thank you very much, Professor Gopal, for your very lucid and interesting presentation, in which you had presented the soil structure interaction problems in a very, and we learned many things from your lecture. Now I will request my co-chairman, Dr. Krishna, if he has some questions or observations.
Thank you, Professor.
Dr. Ramakrishnan.
Yes, sir, I'm here. Yes, sir. I request the audience to post any questions that you have in the online platform, in the 3D platform. On the top left, you can see a question and answers box. You can click that and type in your questions real time. If any of the audience have any questions, please feel free to type in your questions now. Thank you. I think probably the questions will follow towards the end of both the sessions. All right.
Even if there are any questions from panelists, they can also.
Yeah. Any questions from the panelists? All right.
People must be having evening tea.
Professor Gopal, I am having an observation. Actually, when I was working with the soil interaction problems, I was feeling one difficulty. Say, what amount of the soil should be taken into account?
This is
the mass of the soil plays a very important role in these problems. So you can model your interface, you can model many things, but what about the quantity?
That's a very interesting question. One thing we did not in the presentation I made today, but I had an interesting master's student a couple of years ago called Jing Dong. And one thing we looked at was to try and back calculate the response by keeping the mass of the soil as a variable. And she came up with quite interesting figures. Normally, I was kind of expecting something like, say, you got the mass of the structure just as a raw mass, and work out how much soil you, by rule of thumb, will participate in the vibration with the structure, like you would do in a, say, machine foundation case. You would get, I was always under the impression it probably will be a factor of 20 or 15, a big number like that. And once we done this centrifuge test, and we basically, what we were trying to do is to see how the response changes if I keep changing the mass of the vibrating mass of the structure, and see how the natural frequency it changes from being a fixed base natural frequency. And that should be how much soil participates, because I have a good feel for the stiffness. So the natural frequency I can interpret as the change in the amount of soil mass participating. And her numbers were coming about 5 or between 5 and 7, which is very interesting to know. But I must qualify that statement with the vibrations she was applying were fairly small, because we did not want to get into the really non-linear range of the soil, because then the stiffness also changes quite dramatically. The big problem with soil liquefaction is that if you at full liquefaction, you are expecting almost no stiffness. So you're kind of moving the system from having a very noticeable high natural frequency towards something that has almost no natural frequency. So it's just going to fall over. So because your stiffness is changing so much, how do you simultaneously track how much soil mass is participating with it is a tricky problem. But for small amplitude shaking, our experiments are suggesting somewhere like between 5 and 7. But for larger amplitude, it's still an open question. It's an excellent question. It's a bit like damping in the soil. Not many people have a good firm handle on damping in the soil either. Again, for liquefied soil, we are getting damping values between 20% and 30%, which look quite big, but that's what the data says. As the soil liquefies, you get a lot more damping. Maybe I can see the Q&As here.
Yeah. Professor, we have a few questions in the Q&A.
Yeah.
Yeah. So, one question is, how accurately the centrifuge tests can capture the real field conditions? Can it be quantified? How about the soil particle size scaling?
That's a most box standard question for me. First, let me deal with the soil particle issue. Okay, everybody asks this. Why are you not scaling the soils? First thing is, if you scale the soil particles themselves by say a factor of 50 or 100, then your soil classification changes from being say fine sand to maybe silt or something. If you reduce the size of a fine sand particle by 100, it becomes fine silt. So that's not, and then the constitutive behavior changes. So that's not the way to go. My first question is, in soil mechanics, we always treat soil as a continuum. And that's the basis of any finite element analysis. Other than the discrete element modeling, every other modeling technique we have come up with to analyze our problem assume that the soil is a continuum. So if you assume that the soil is continuum, then we are basically doing the same thing, except that we haven't got, instead of millions and millions and millions of particles, billions and billions of particles in the field, we got millions of particles in our centrifuge model. Okay, it's a factor smaller, but we got sufficiently large particles. I could simply say that, well, we got, my professor Andrew Schofield always used to say, one centrifuge test is like doing 10,000 triaxial tests. If you look at how much soil you have in a triaxial sample and see how many particles there are in a centrifuge model, it's a factor of at least 10,000, if not more. So we have a lot more soil than in the field. In terms of inclusions, say you want to look at the soil structure interaction, which is what I was talking about today, then you must make sure that your anything you're inserting into the soil has enough particles to be in contact. If you follow, say, Fumio-Tsuchioka's shear band theory and how many particles are required to form the shear band, he suggests that must be at least a factor of 15 or 20. So as long as your inclusion has, say, 50 or more particles, the fact that you got a lot more particles in the prototype doesn't matter. And you can check that.
Thank you once again, itself. Professor Gopal. Let us wind up this one. Okay. Okay,
so that's the quick answer for that. In terms of modeling to realistic conditions, we are getting much, much better. Now, for example, the last project I was talking about has a clay layer, a liquefiable layer, and a coarse sand layer. But if you're in the field, you normally get a lot of heterogeneities and stuff. You don't want to include that in a centrifuge model because at the end of the day, you want to have a repeatable model. But the number of layers we are increasing and we are making more and more complex models all the time.
Professor Somisharan, sir, can we have one more question? We got a number of questions in the Q&A.
Yeah, I can see there are some very interesting questions. One by Kuli. The structure beside the wall has been simplified into a portal frame with its footing resting on the surface and analyzed. No, the footing was actually embedded into the ground. My question is, how did you take into account effect of earthquake on the wall due to the embedment of the structure's foundation? We don't have to. You create the whole model, apply the earthquake at the foundation, and what will happen is what we observe. So all that is accounted for automatically, both in the finite element analysis as well as in the centrifuge. So that's all. Because our finite element analysis is in the time domain, all we need to do is to make the mesh. The constitutive models are the complicated part of it, but I haven't got the time to go into that today.
All right. Thank you, Professor Gopal Madhushi. Sir, I think we lost Somisharan, sir.
Maybe you should take over and introduce the second speaker. Tohata is waiting there patiently.
Yeah. I think Professor Somisharan
some of these offline. I think, am I able to do that? You think?
Yeah, you can actually type in and Yeah.
Okay,
You can
I'll do
use
that.
Professor
while-
Ravi? Ravi, sir? Professor Ravi?
Yeah, you can see.
Yeah,
Ramakrishnan,
he
you
can type in the answers, right?
Yeah, he can
Yeah,
answer.
all right, great.
That would be better.
So,
Actually, there is a
I would like
project
to,
immediately after this at 6:30. So please continue.
yeah, all right. All right, so I would like to introduce the next speaker, Professor Iko Tauhata from the University of Tokyo. So Professor Iko Tauhata is a Professor Emeritus, University of Tokyo, and was distinguished visiting professor at IIT Bombay, India, till December 2016. As a JICA expert, IIT Hyderabad in India till March 2017, and is the president of Japanese Geotechnical Society from 2014 to 16. And he served as the vice president for Asia, ISSMGE, 2013 to 17. His major fields of interest are deformation characteristics of cohesionless soils, dynamic analysis of earth structures during earthquakes, permanent displacement of ground caused by seismic liquefaction, soil improvement by densification and grouting, microscopic observation of granular behavior of sand subject to shear, and dynamics of landslide and debris flow, etc. Recently, Professor Iko Tauhata worked on recovery and retrofitting for future of infrastructures on residential islands, river levees, and Fukushima #1 nuclear power plant that were damaged by the 2011 Tohoku gigantic earthquake, liquefaction, and nuclear disaster. Professor Iko Tauhata has got more than 400 English papers in international journals and conferences, including a comprehensive book on geotechnical earthquake engineering. I would like to welcome Professor Iko Tauhata. We are very glad that you are here today, and we are waiting for you to deliver your lecture. Thank you. Over to you, Professor Tauhata. I think, sorry, I think you are muted.
Demuting. Okay.
Yeah.
Thank you very much. Thank you very much for your kind invitation. And actually, I missed the opportunity to visit India this time. I cannot go. I was thinking to first attend this conference and then go to Ooty and enjoy toy trains in the mountains, but nothing is possible. So as a compensation, I have this nice cap. I got this one from in Pune. So I put this on as a compensation, this direction. Yeah. And then try to deliver this lecture. So let's share my presentation. Then start. Okay. Okay, you can see this picture, right? Okay, let's start.
Yes, sir. Yeah.
Okay, my title is the history of liquefaction mitigation technologies in the past 60 years. And I'm trying to show that the target of technology has been changing from time to time. Initially, the target was very relatively easy situations, but nowadays in the 21st century, target is much more complicated and difficult, and engineers have to be very careful about success of the project. So content is like this. I start with this overview of his history, damage. Then briefly, I'll talk about causative mechanism of liquefaction and principles of mitigation. Then mitigation measures for newly constructed structures. This is one of the easiest situations. However, there are two types of technologies. One is prevention of liquefaction. The second one is allowing for some limited extent of liquefaction, but without much damage. Then I will move on to existing structures. This is more complicated and difficult than new construction. And certainly the two technologies, one is just prevention, the other is allowing for limited extent of liquefaction. Then existing houses are very difficult target of technologies. And there are two groups. One is groundwater lowering. The other one is underground grid wall. Then I briefly talk about emerging topics and miscellaneous issues. That's my idea. So overview of past damage was like this. Actually, liquefaction did occur many times in the history, 1,000 years ago, 2,000 years ago. But in those days, liquefaction was not a disaster. It was just a phenomenon. However, human activities expanded into difficult soil conditions in the 20th century. So liquefaction changed from phenomenon to disaster. This is one of the earliest experiences in Niigata 1964. Maybe this is very famous as a tilting and falling down of apartment buildings. Certainly there is no good foundations under the building because sandy ground was considered good foundation soil in those days. However, liquefaction resulted in loss of rigidity, and there was no more bearing capacity in foundations. So this disaster happened. 1995 Kobe earthquake was like this. A harbor was destroyed by liquefaction and the lateral movement of gravity key walls. So harbor operation stopped for 2 years. So this is an important example of business continuity planning. We should work not only on the safety factor, but also on economic aspects of disaster mitigation. And this is a measured acceleration, horizontal acceleration in the liquefied area. So top 16 meters was made of loose liquefiable sand. So within that 16 meters at the top, acceleration decreased drastically, as shown here. Both horizontal and vertical accelerations decreased drastically within this liquefied soil. Then 2011 Turk earthquake had magnitude 9. It was gigantic earthquake, and many things happened. This is one of them, floating of light underground structure. This building was actually a parking space underground, but this entire structure came up to the surface. And another phenomenon was the sand ejector or sand boiling here. This is evidence of liquefaction on the surface. And this is enlargement. So you can notice that slope movement occurred like this. Maybe this movement is similar to circular slip movement. Slope moved downwards and the bottom part uplifted. So during liquefaction, groundwater pressure becomes very high and the effective stress is lost to 0. This means shear strength, sigma dash into tangent phi, becomes nearly 0. Therefore, slope moves like this. And recently, about 3 years ago, Indonesia suffered this astonishing disaster related with liquefactions. These 4 slope failures occurred like this, and lateral displacement was as much as 500, 600 meters in the horizontal directions. And many houses moved downslope, and houses were destroyed. And in those houses, more than 1,500 people are killed. So before this event, everybody believed that liquefaction does not kill. But nowadays, we have to say liquefaction kill people like this. And it was unbelievable that the slope gradient was only 2%. Yeah, in the past, liquefaction did happen in 2% slope, but displacement was limited to 5 meters, 10 meters only. So why 500 meters? Still, we don't know why. Is there any special conditions in this island or Sulawesi in Indonesia? This is a question. If there's no special things in this island, then liquefaction should have induced 500-meter displacement in 2% slopes in many parts of the world in the past. but it never happened in the past. So I still suspect there was something special in Sulawesi Island. And some people have been talking about the effects of irrigation canal. Okay, in the map, I show you 5 sites of lateral flow: Bararoa from top, Petobo site, and Roru site, Jono Oge site, and the Shibaraya site. And there is an irrigation canal over here, and this is a picture. So this canal was not paved at all. So water was able to infiltrate into the slope, top of the slope. And some people say this water infiltration triggered 500-meter slope movement. This is a very easy idea. However, another one, remaining site, Bararoa site, was like this. At the top of the slope, there is a residential area. There is no canal. This is important. So also, this is 6 weeks after the disaster, and headscarp cliff is dry. So this means that water infiltration is not the main cause of 500-meter lateral flow. Most probably, infiltration just increased the extent of lateral flow, but not the cause. It was not the causative mechanism. So why does liquefaction happen? This is a well-known problem. So essence of liquefaction damage is actually large ground deformation. Shaking is actually reduced by liquefaction, but the residual displacement deformation is the essence of damage. So because of large deformation displacement, serviceability of facilities is lost. But I used to say nobody is killed, but now I have to say many people may be killed, unfortunately. So this is a well-known mechanism of liquefaction. This is a loose packing of grains subject to horizontal cyclic shear stress. And grains falls into big voids like this, and water is pushed out towards the surface. So water pressure is pressurized and drained out towards the surface. According to the Darcy's law, water flow takes 30 minutes or longer to reach the surface. So in the meantime, water pressure is held high, effective stress is lost, and large deformation happens. So liquefaction is prevented or mitigated by changing the story shown above, shown here. So there are several kinds of liquefaction mitigation technologies. First, loose packing of sand particles is a cause of liquefaction. So we need to compact the grains. This is the first idea. Second one, falling or moving of particles into big voids. This story is changed by bonding or grouting of grains. Significant cyclic motion particles is reduced by mechanical constraint against ground motion. Long time is needed for drainage, so why don't you accelerate drainage procedure by installation of gravel drains, stone columns, by which through which water can flow quickly towards the surface. Also, some people say incompressibility of water is a problem. So, okay, why don't you remove water from the ground? Well, why don't you inject gas bubbles into soil? So, by taking any one of the options here, you can mitigate the liquefaction hazard. So, mitigation measures for newly constructed structures by preventing liquefaction. For new constructions, actually, we don't have to worry about trouble by existing structure. There's no underground obstacles. Ground deformation, vibration, noise, etc. are allowed. there no complaint in a open space. So compaction densification was the earliest technology to mitigate diffraction. But we try to increase the standard penetration test M value to hopefully 20. So after compaction, now little pore water is drained out, diffraction is unlikely, and the first technology of this type was vibro-flotations. Actually, in Lapronia, USA, started vibro-flotation technologies. But in those days, his target was not the earthquake problem. He tried to just improve static performance of sandy ground, and he was successful. And this technology was applied to earthquake problems in Japan in 1950s. It was 7 years before the Niigata earthquake, and it was quite successful. On your left-hand side, tank foundation was damaged because sand was not compacted, but on your right-hand side, vibro-flotation successfully protected the tank. Then problem was heavy noise and vibration of the ground during vibro-flotation or other kind of dynamic compactions. I remember that I was never able to communicate with colleague people within 30, 40 meters from compaction machines. Therefore, static type of machine was developed. No vibration, but machine rotates like this and moves back and forth in the vertical direction and push new sand, new material into loose sandy ground. Intrusion of new volume of sand means densification of original sandy ground. And this is just the idea of the vibration intensity. 20 decibel reduction is very, very possible. So nowadays we can easily talk with people within 5 meters from the machine. A good point of compaction is that no maintenance is necessary after ground improvement. You can just forget deterioration or aging or whatever. However, soil moves laterally because of this compaction. Therefore, soil movement may affect existing structures within, say, 5 meters. So we should avoid working compaction within, say, 1 meter. Anyhow, experience verifies the performance of technologies. So this is an example of static quiet compaction during 2011 Tohoku earthquakes. In one construction site near Tokyo, nearly 70% had been already compacted, 30% had not been. So you can easily recognize different performances. On your right-hand side, still there is water ejection from the ground. I mean, oops, too small. There is a pointer. This part. And now ecology is a very important issue in our world. So now in place of gravel or sand, now some companies try to push timbers into soil. This is an ongoing project near Tokyo. First, hole is drilled, then timber is pushed into soil, and the top is just capped by bentonite powders. Actually, ideally, just we wish to drive timbers into ground. This is the easiest compaction. However, noise problem does not allow us to do driving. Dynamic driving is not allowed. Therefore, first we have to drill a hole like this by screws. Then we have to statically push timber into soil. This is more time consuming, but now environmental control is very, very strict against noise, construction noise. Local people hate it. But anyhow, timber is good for environmental protection. So consolidation, dynamic consolidation is another money-saving technologies. Already many years ago, French people verified that pressure meter data is increased by this dynamic compaction, dynamic consolidations. This is much cheaper because we don't have to push machine into the ground. Just surface is tamped by heavy weight of concrete. And this technology was verified as a good liquefaction mitigation technology during Chichi earthquake in Taiwan, 1999. This section was not yet compacted and the liquefaction happened. This section had been compacted, so no problem happened. And the SPT M value increased significantly like this. So now we can trust dynamic consolidation, but noise and vibration is the issue. So, people used to love quiet technologies in early 90s. So grouting was developed. This is mixing cement and sand by machine rotations. So in those days, 100% soil was mixed with cement. So this is quite expensive, but quiet, no vibration was produced. So this technology was accepted in developed urban area, but money was the problem. So as a cost-saving technologies, grouting in grid shape, grid configuration was developed also in early 90s. So now only grid part is mixed with soil, cement is mixed with soil there. So remaining part is just soil. So this is much cheaper. Only 30% of soil is mixed with cement. And this technology worked quite well during 1995 Kobe earthquake. There is hotel in Kobe Harbor, and in the surrounding area totally liquefied, but this building foundation was intact. No problem happened. So this is a photograph on your right-hand side during construction, installation of grid walls. So you can recognize that cement columns are installed and they are connected with each other and formed grid wall. Size is 5 meters, 7 meters, 10 meters, something like that. So what is the mechanism of this grid wall? Actually, cyclic shear is the procedure toward liquefaction. Greater shear strain means more chance of liquefaction. So idea is, why don't you decrease this shear strain by installing rigid wall like this. So actually this mechanism is different from that of 100% soil grouting anymore. This is constraining shear deformation. So most important issue in this technology is the wall interval. 30 years ago, Public Works Research Institute Japan did many model tests and decided that interval should be less than 70% of the thickness of liquefiable soil. So as an interpretation of model test, 70% was a good idea, reasonable, no problem. However, then practical people started to interpret this 70% rule in a different way. According to them, bigger design earthquake creates greater thickness of liquefaction from 3 meters to 10 meters. Then 70% of thickness also increases. Therefore, wall interval can increase during stronger, bigger design earthquake. This is nonsense. So nowadays, for practice, engineers carry out dynamic analysis, finite element analysis, nonlinear analysis in order to determine the wall interval. Then technology like this, pre-mixing soil cement before reclamation. So this one worked quite well in 2003. Pile foundation is often attractive as a good, useful, safe building foundations. In 2011, Tohoku earthquake, pile foundation successfully protected the building, but problem is consolidation settlement in the surrounding soil. After ejecting lots of groundwater, liquefied sandy ground subsided 30-40 centimeters. This means connection of lifelines for water, sewage, gas, electricity, communication are cut. So consequently, this building became useless. So for money saving, sometimes we allow for some limited extent of liquefaction, gravel drains or stone column is the most famous example. And soil is no more undrained and with these gravel drains. Water needs to travel horizontally by only 80 centimeters and quickly dissipated to the surface. So low effective stress 0, continues for only 5 seconds, 10 seconds. So during such a short time, ground cannot deform very much. So in this way, we can keep serviceability of structures. Also, this technology does not cause vibration, no noise. So near very humble wooden structures, we can do this technology. So this example after Kushiro earthquake 1993, this is my graph. And certainly subsidence happens because water is drained out. But this is small, only 10 centimeters, 15 centimeters. So we can easily repair this by overlaying asphalt at the surface. So this is not damage. Maybe some people are worrying about clogging effects. Silty sand may come into the gravel drains and closes the space. So afterwards, gravel drain does not work as a water channel anymore. So people were worried about this problem in 1980s. So full-scale shaking model tests were conducted. So you can compare the sand, the silt content in the horizontal direction. This part, 0 centimeter to 20 centimeters. This is a part of gravel drains. So and outside is just native sand. So actually, what should I say? Sand content, so silt content did not change very much after shaking test. So we came to believe that migration of sandy, silty content is quite small or negligible. Only here we have just one, some increase. So, and the performance was very good in 2011 earthquake. Here, gravel drain was installed, so no damage happened to this river levee. But without gravel drains, big damage happened. And this is a cross section. There were many gravel drains like this. And this is a very important principle of earthquake-resistant design of river levees. Flood and earthquake do not come together except near the sea. Near the sea, high tide means flood twice a year, twice a day. So we don't have to worry too much about deformation of levees caused by earthquake. We have some weeks, several weeks before flood comes, so we have time to repair the damage. So we don't need 100% safety for river levees. Quick restoration, maximum 2 weeks. This is the target of my government policy. So this is very, very possible if subsidence is less than 1 meter or maybe 2 meters. So we have this important empirical relationship from experiences from 1890 to 2011. Empirical relationship between levee height, H on your left-hand side, versus S, this is subsidence. So in the diagram, horizontal axis shows the original height, vertical axis shows the subsidence. So all data staying under this 75% line. This means in the worst case, 6 meter levee still keeps 1.5 meters height because maximum subsidence is never greater than 4.5 meters. So if this remaining 1.5 meters good enough to stop 2-week probability flood, then we have time to repair this levee for 2 weeks. So in this way, actually significant subsidence damage is still allowed from a probabilistic viewpoint. It's a pity for me that nowadays market share of drainage is decreasing. 1993, this much of share was occupied by the drain, but the share has been decreasing 11 years later, while other technology, densification, grouting, increased drastically. Why? Because in the design calculations, engineers want to keep effective stress in this part more than 50% of the initial value. This means water drainage should occur very, very quickly. So that's why interval between gravel drains, say only 1.5 meters. But after 1995 Kobe earthquake, actually design earthquake became even stronger. So design calculation of drainage or Darcy's law could not keep effective stress more than 50% anymore. So engineers, government engineers, officers actually gave up gravel drain technologies. But it's important that 2011, gravel drain still worked very well under this magnitude 9 strong earthquakes. Shaking here was 2 times stronger than design intensive motions. So actually this technology has something more than just drainage. I mean, gravel drains with good rigidity can keep the entire ground intact. This is mechanical reinforcement. But now current design principle does not think about this mechanical rigidity. Only Darcy's law is calculated. That's a problem. So human knowledge is still not enough to understand everything. And this is just the experience in 2011. House resting on liquefiable sandy layer becomes like this. Entire house sunk into subsoil. And Professor Asada studied house damage in 1980s, and he proposed that good thickness of H1. H1 means crust. No liquefaction happens here. If this H1 is good enough, big enough, house is protected. House does not undergo any damage, even if we have thick liquefaction soil, because of this punching failure mechanism. This red part, another red part, develop good shear resistance, and this is good enough to support the weight of light structure at the surface. So in line with this, after 2011, government decided to use this diagram as a guideline on house safety during liquefactions. So if H1 is greater than 5 meters, this ground is considered good, whatever liquefaction risk is here and in the lower layers. So in residential area, we try to achieve 5 meters, or sometimes 3 meters as a target of surface compaction. Then after 3 meters or 5 meters, we can forget any problem underneath. So this is for money saving. Yes? Okay. So this is
Professor Tohata,
yes.
please wind up within 5 minutes.
5 minutes. Okay. So under existing structures, okay, 5 minutes. This is called compaction grouting, pushing grout into soil, and this machine is small enough to work in the basement. Machine is very small. And this is another type of injection of colloidal silica. This is expensive, but machine is also small. It can work in the oblique directions, so we can improve soil under existing structures. This is very important nowadays. And some people are worrying about aging effects of colloidal silica. They say after 10 years, 20 years, silica may be deteriorated. But no. If the material is good enough chemically, okay, this evidence, unconfined compression strength after 5 years, 10 years, 15, 20 years, kept intact. Also liquefaction resistance in the first 3 years is like this, but after 10 years, it's maybe 2 times higher. So aging problem is not there. So now, okay, this is for technology for existing structures. I mean river levees. Levee deforms like this, but if we install sheet pile wall here, subsidence is reduced. So this is a practice. Okay, now sheet pile wall is installed along the foot of this slope. But problem is environment. Groundwater environment may be disturbed by this impervious steel pile. Therefore, holes are open like this. This is passage of waters. Also, floating of pipelines problems. So this is technology to stop the floating. So house is the most difficult target. In New Zealand, no improvement anymore. Relocation to safer place is a choice. But Japanese people don't want to move. They want to stay at the same place. So this house, okay, for this house, water was drained out like this. So dry soil, dry sand does not liquefy. So let me skip this one. Okay. Okay, this is ongoing drainage from a residential area. So this is successful. Also, this is also another project. Drainage pipe is installed here. So groundwater flows in horizontal direction and groundwater level goes down, and surface 3 meters or 5 meters are made intact. My experience of this one, groundwater lowering may trigger consolidation in the soft underground soft clay subsoil. Sometimes we have clay layer, sometimes sandy layer, but we have to improve entire residential areas. So groundwater lowering is not accepted in this area. As an alternative, we installed grid walls in vertical, horizontal directions like this. But this is very difficult because the space is so small, costly as well. So we did this. Let me skip this. So emerging topics. Lifeline is actually a very difficult target because lifeline industries don't have enough money to improve the entire ground. Also, even those lifeline authorities are not allowed to touch soil except in the backfill area. So this area is never enough to protect the lifeline system. So I propose this type of mechanism to prevent floating of pipeline like this. And another technology is installation of many columns to prevent big lateral flow. Blasting is another technology, but I failed to achieve SPT value 20, only 18. Mixing with tire chip is good. Kobe, so this is very interesting. Liquefaction occurred entirely in this island. And but in the central part, no liquefaction happened. But actually only this part, vibro compaction. This blue part was intentionally improved against liquefaction. Other part was just installation of sand drain preloading for mitigation of consolidation problem. But during construction of sand drain preloading, heavy machines moved back and forth here, and it affected the density of surface soil. So consequently, no liquefaction happened. So this is unintentional mitigation of liquefaction. So miscellaneous. We need to find rich customers. Actually, house foundation was not a very good target because people don't want to spend much money. We wish to help people directly, but they don't want to be helped. This is a problem. So where is a rich future customer? This is my question. So time is okay. Many thanks for your attention. So this is the end of my presentation. Thank you very much to Pune.
Thank you, Professor Tohota, for a very nice lecture of practical importance. We are very grateful to hear a very nice lecture from you. Now, Dr. Krishnan, have you collected some questions?
Sir, I'm still waiting for the questions. Dear delegates, please feel free to type in any of your questions into the Q&A box in the 3D platform at the top left of your window. I have one, not a question, I have one comment saying that it's an excellent session. Of course, it was an excellent session, Professor Tohota. And I think we will have more questions coming in a few minutes. In the meantime, do we have any questions from the panelists? Do we have any questions? I don't think we have any questions as of now.
Okay. It's 10 p.m. in Tokyo.
May I ask one question?
Well, oh yes, please. Yes.
Thank you, Professor Gopal, for typing in the answers for all the questions that have been raised by the delegates.
That's okay. It's my pleasure.
Thank you, sir.
Somebody had a question.
Professor Swami Sharan, sir.
Question.
Over to you, sir.
Yes.
Yes, I think
Paru.
very nice. Both the presentations were excellent and very effective.
Yeah, actually. Okay.
Speakers very much.
Yeah. May I answer
Anything
that?
you want to convey, Professor Paita?
So may I answer the second question? Yeah, second question addresses Paru lateral flow during earthquake. First, I said that water leakage from unpaved canal just promoted the displacement, but it was the main trigger of a big flow because one side, Bararoa side, did not have irrigation channel, but still big deformation happened. So what is the cause? Actually, I have been working for the research team under Japanese government, and the researchers proposed many ideas. One famous idea was water film formation. Water film. Water is drained out from liquefied sandy layer, but could not reach the surface because surface soil was less pervious. So water remained between surface soil and liquefied sand. So water had no shear resistance. So surface soil just flowed in the horizontal direction over 500 meters. This is very possible. Many shaking table tests, centrifuge tests verified this idea. But basic question is such a simple situation should have happened many times in the past. Actually, such a 500-meter big displacement never happened in the past. So this water film theory is too simple, too possible.
Professor Tawhat, I think
yes.
it's possible that the water film forms, but it's very difficult to sustain it for a long period of time because it will always find a way to drain.
Yeah. Water film flow lasted several minutes.
Yeah. So it can trigger the triggering event could be water film.
You are right. Yeah, you are right. Your point also important. So second idea, my idea was actually all lateral flow happened between big old alluvial fans. Alluvial fans are deposit from valleys. So alluvial fans all often include artesian water pressures. So my idea was strong shaking destroyed the underground aquifer, pressurized aquifer. So lots of water flowed into the slopes. So water was supplied into ground. So in this way, I was able to avoid the problem of sustainability, as you said. And another idea is actually, there are old faults under the slopes. This time, those faults did not move, but it's geologically possible that deep water, geological water, comes to the surface during earthquake. So this is another source of water supply. So basically, there are three ideas. We are fighting, academically fighting, but we could not reach any conclusions. So this was academic fighting for 2 years, but nobody won the game. So now I'm going. Another question.
Yeah, we have a few more questions.
Okay.
Sir, have you ever used diaphragms for liquefaction mitigation?
Okay, yeah. Any experimental evidence of performance of home mitigation? Yes. I already submitted several years ago to Soils and Foundation Journal. So if you want to know the reference information, please send me email. first author is Otsubo, but I'm certainly one of the authors. Then in one of the slides, there was one recommendation of improving the soil only until 3 to 5 meters under the building. Can you share the reference for that recommendation? Oh, yes, yes. Actually, Professor Ishihara, Kenji Ishihara, showed this idea in 1985 during International Conference Soil Mechanics Geotechnical Engineering in San Francisco. It was 36 years ago. If you need more information, please send me email. And please don't misunderstand that you can construct a heavy oil tank over 3 to 5 meter layer. No, tank is too heavy. I'm talking about just house.
So is there a recommendation on how much bearing pressure the structure should be limited to? Maybe 20, 30 kilopascals or something like that?
Yeah, something like that. 2 tons per square meter, something like that.
Yeah, that will be about 20,
only. No,
yeah,
don't
20,
think about tank. And then next question. Can you please name few geological stones which can be mixed to avoid geological stones? Maybe this person, Mr. Wahid, showed it. He means gravel drains or stone columns. If so, I would say mudstone is not good because mudstone becomes just mud after years. But sandstone may be okay. And then next question.
Tire chips.
Use sand tire clamps for liquefaction. Oh, yes, yes. Actually, your colleague, Indian colleague, Professor Hazarika.
Hazarika,
he loves tire tip technologies. I did only one shaking table, only one time shaking table test to confirm the tire tip effects. But maybe nowadays Hazarika is a more suitable person to talk about this issue.
I think he'll probably will. He has a keynote lecture later on, so I'm sure it'll come up.
Yeah. Then, so please. Oh, that's all. That's all.
That's all.
Yeah, thank you very much for your attention.
Okay. Thank you very much. Now we came to the end of the session. Now I'm requesting to Professor Jaka if he wants to announce something.
On behalf of organizing committee, we thank both the keynote speakers, Professor Gopal Madhubushi and Professor Tohota, for kindly accepting our invitation and delivering today's excellent lectures. Thank you both. Thank you both. And I also thank, on behalf of organizing committee, our chair, Professor Swami Saran. In spite of technical difficulties, he managed very hard to attend our session and handle it. Thank you very much, sir. I also thank co-chair, Dr. Ramakrishnan, for effectively managing the session. Thank you one and all. And now there is, after a few minutes, grand cultural event is going to be start, and our colleagues, Dr. Parthasarathi and Dr. Srivalsa, made a lot of efforts for the cultural evening. So I request all of you to join and experience culture, Indian culture. Dr. Parthasarathi and Dr. Srivalsa, please, if you like to add, please add.
Yeah, please, during this pandemic time, it is time to relax after a long technical session. So please join us with your family. In few minutes, we will start with the wonderful performance, dance and music. So rejoice, enjoy, relax and be happy. Please join us. We welcome all of you.